good afternoon, or good evening to everyone joining us today for this webinar. We would like to thank Gareth Wood, our invited speaker, the EAGE technical community on wind energy for organizing this event, and all of you for being here. We hope you enjoy the session and learn a lot. And with that, we will begin the webinar. Katie, I hand it over to you.
Great, thank you very much, and welcome everybody. As an agenda for today, first of all, we're going to have a quick introduction about our EAGE technical community on wind energy. Then Gareth Wood is going to provide us with an overview of geohazards and geoengineering constraints to wind farm development on formerly glaciated margins. And then if you've got any questions throughout the presentation, please just type them away in our Q&A box, and we'll have a session at the end before we close. So just a brief introduction about the EAGE technical community on wind energy. We're a network of members who are interested in sharing knowledge and developing skills amongst geoscientists supporting offshore wind energy. We come from all over. There's all sorts of people in the community. We're established in 2024, and our count is currently at over 1,120 members, and it's growing very quickly day by day. So if you're interested, there's numerous of us on the committee. We're spread throughout the globe. Please get in touch with any of us to find out more. And if you'd be interested in joining the committee, put yourself forward. We're always happy to including more people within the committee as well. We do loads of different community activities across the year, particularly the EAGE annual conference, the GET conference, and many other events. We have dedicated sessions, and then we've got an upcoming dedicated session that Benjamin Bellward's leading for the EAGE annual, and also participation for the GET conference, which is coming up as well. We've got, I think, an extended abstract deadline of 15th of June for that, so please get your submissions in for that if you are interested. We have other educational networking events and collaborations such as this one that we do throughout the year, so keep your eyes peeled for that. We're doing these bi-monthly at the moment, but if we get more interest, we could run them more frequently. So if you have any ideas for any other webinar titles, please put yourself forward. We'd be very happy to have you. And we also have our LinkedIn site where we have news about careers, advice, general news and vacancies on there as well, so please join us. And if you're interested in that, we've got our LinkedIn QR code here. If you want to have a quick scan of that, please do come and join us on LinkedIn and build the community further. Brief plug for EAGE annual coming up in June this year, 8th to the 11th of June in Aberdeen in the UK. We're running a dedicated session, so please put yourself forward. We'd love to have you, as well as at the GET as well, which is in Hanover in November. So two really big, great conferences coming up, and we have a specific offshore wind energy conference within that larger event. So it's going to be a really good event. So yeah, thank you for joining our webinar, and without further ado, we'll move on to Gareth to give his introduction. Thank you very much, Gareth. I'm really excited about this.
No, thanks, Katie, and thank you everybody for joining. It's been a real pleasure to see so many people sign up. It's fantastic support for our community, and I hope you enjoyed the presentation. I'll just go ahead and find the share button again, which I've just lost. Yeah, a little bit about myself. For those that don't know me, I've been around now for 31 years in the site investigation industry. Started off as a geologist at Leicester University, doing a degree there, and then went on to do a Masters in Marine Geotechnics at Bangor University, which is one of the mainstays of staff coming into the site investigation industry from the 1990s, and so sure several of us are here. Fugro, or Geoteam Wimpole as it was called, in 1995. I worked as an offshore geophysicist for a few years working on a whole variety of different projects, submarine cable projects, pipeline projects, lots of different types of engineering, and also lots of oil and gas projects as well, all across the globe. And then I came to BP in 2007. Been here ever since, with a short stint in Houston. But in the last sort of 4 or 5 years, I've taken on the sort of technical advisor role for geohazards in the company, and been exposed to some wonderful projects. And certainly in the last 4 or 5 years, got myself involved in the offshore wind business. Absolutely loved it. Still do love it. Really challenging and such a great community to work in, and that's why I'm here today to perhaps show off some of my experience and hopefully knowledge that might be of interest to you. As you can see, the title here is Overview of Geohazards, Geoengineering Constraints, Wind Farm Developments and Formerly Glaciated Margins. Before I go anywhere, though, to sort of say this is not my work by any stretch of the imagination. So what we're showing you today is basically a collaboration between all of these people here, led by our Sir Benjamin Belwold, our master of presentation and reviews, who had this brainchild of pulling together this group of people to write a review paper on geohazards and geoengineering constraints. We have a working draft, shall we say, of the manuscript. We are in the process of working out the best way to get it out to the community in the best way possible, and that will hopefully be sometime in the very near future. So yeah, by all means, this is not my work. This is just a showcase of all the work that we've been pulling together for this review paper that we hope people will find useful in the future. So, as we probably know, or most of us know who work on glaciated margins, they are highly complicated settings linked to ice sheet dynamics, resulting in spatially and temporally heterogeneous glacial and interglacial sedimentary cycles, which are then affected again by repeated ice oscillations, sea level changes, and then essentially glacial acidic rebound on final retreat. The resultant seabed and subsurface is therefore very, very challenging to engineer around, and certainly to operate renewable energy infrastructure at scale. So, as I said, we're taking examples from this review paper this time around, and I'm focusing more on engineering constraints than geohazards, and I'll come on to that reason why I call it that in a minute. But what I have tried to do is try to find a few examples of where I think these constraints will have engineering significance, and we've got a couple of showcases to demonstrate that. So the reason we started looking at this review paper was we suddenly realised, or everybody knows, about this huge expansion of all types of projects going on in the North European continental shelf. This map here on the right demonstrates the number of projects from oil and gas to wind farms and to carbon capture projects that have exploded in, let's say, the last 20 years. And nearly all of these are on or dealing with some form of glaciated landscape and soils of some form. So I guess the industry, as far as I'm aware anyway, started way back in 1964 when we had our first geohazard-related event in the German sector, where the jack-up barge Mr. Louis, drilling well B1, suffered an underground blowout after drilling a gas pocket. Thankfully, nobody was hurt. The rig itself was relatively undamaged, but it did end up with an eruption of gas and mud that blew out the seabed and came up to the sea surface about 400 meters away from the rig. So that was really the first sort of indications that, okay, this is not as straightforward as it might be, engineering in this type of soil. And there have been a number of incidents in the oil and gas industry since then. And as far as I'm aware, and somebody can probably tell me if I'm wrong, but as far as I know, that the Vindeby offshore wind farm in Denmark in '91 was our first at-scale offshore wind park in Europe. and since then, it's just gone ballistic. We've got very, very large projects ongoing at various stages. It's a very exciting time to be in the offshore wind business, and hopefully we can get all of these projects in the ground with minimal sort of impact on engineering and costs. So all of these projects have had a variety of sediments, landforms, and hazards that they've had to negotiate around, and some more successfully than others. One of the big challenges that certainly I tend to use maps like this quite often is just the sheer scale of the developments that we work on in the offshore wind business. I've chosen Sophia here as a relatively, I guess, standard size, although in recent years they're getting bigger and bigger. But to put it into context, the site investigation implications on foundations for an offshore wind project, for example, are in excess of 40% of the total project costs. So that's an awful lot of money that you have to put in to put things into the ground. And therefore, getting that ground prediction as uncertain or certain as you could possibly get, reducing those uncertainties is critical. And if you compare that to an oil and gas project where, let's say, the income from those projects come a lot faster, it's less than 5% of the total project cost in terms of foundation design. So there's a lot of emphasis on us as geoscientists and engineers to try and minimize our uncertainty through a very rigorous process of site investigation, assessment, and communication. A little bit of terminology as well, just to sort of set the setting, or set the scene for the glacial environments. For those of us who've worked in glacial environments, we use these terms, daily, but some people may not be so familiar with them. We often talk about things being subglacial or proglacial or glaciamarine, and so understanding what that actually means. So anything subglacial is deposited or has been altered because it's underneath the ice. N-glacial means that there's a feature within the ice that is then deposited. Superglacial is on top of the ice. Proglacial is in front of it, and then obviously glaciamarine is material within the seawater in front of the glaciers. And the sedimentary environments here are very, very variable, depending on at what time or what stage glaciation is ongoing, and depending on where you are. Certainly if you're working in the Irish Sea, for example, or Dogger Bank, you're going to see a lot of these types of sedimentary environments: glacial lake systems, fluvial systems, all types of moraines and other landforms. And it's when you sort of look at, I guess, analogs, modern day analogs, like in Iceland or in Greenland and Svalbard, that you can sort of see the juxtaposition of all these different sedimentary environments all next to each other in a very, very small, relatively small area. And so you can get quite drastically different sedimentary sequences with different engineering properties at a very, very local scale. And when you're dealing with engineering at scale, that can become very problematic. Just to sort of re-emphasize and give a few examples of that. So here on the top right, we've got a proglacial system of moraines and ridges, thrust moraines and proglacial lakes. Just to sort of again give you the impression that in lacustrine environments you're going to get relatively soft layered material, whereas the material that's already been overridden by ice is going to be quite hard and variable. And then just the sheer scale of some of these sedimentary systems, these fluvial systems. There's a outwash plain or an outwash fan here in the center, and then this is a sander plain from Iceland. Which some of these features can be extremely large indeed and go on for many, many tens of kilometers. That it's also quite important about the type of bedrock that is around in the area. a lot of the material at what we call a basal till, which is usually the subglacial deposition system of an advancing glacier, is built up of the local bedrock. This is an example from the Irish Sea, where literally within 10 kilometers of each of these samples, the actual what we call a glaciotectonite here is completely different. One is made up of primarily an evaporitic mudstone, which is this red material here, completely reconstituted into this glaciotectonite, or till, if you want to call it that. This one is derived from a sandstone, Aeolian sandstone, and this one is derived from carboniferous coal measures. So, like I said, they're all very, very close to each other, but from a property perspective, they're different materials. And then we get very localized landforms of a wide variety, each again with their own unique sedimentary patterns and distributions. And then overlying all of that, occasionally you might get an advance of ice, which then causes the whole thing to be shifted, and you might get some large thrust moraines or push moraines and hill hole pairs. And again, all this is doing is changing the original fabric of the material that was originally deposited, and again increasing that local complexity. Okay, so that's the sort of introduction. I'm going to launch into some of the constraints now, but I wanted to start a little bit with definitions. So I think the industry as a whole is very guilty about chucking everything into what we call a geohazard box. But the phrase geohazards actually probably should be limited to dynamic processes. So things like earthquakes and seismicity. A lot of the static or in situ features that we have to deal with are actually more constraints than actual physical hazards. And so I like Paul Dimmock's definition up here, and this sort of list just goes to show you how wide and varied people's opinions are on what marine geohazard is. But I do like these two here, and I think it is important to, particularly in an engineering project like a wind farm, to differentiate what is considered to be a hazard, i.e., something that may happen to wipe out the entire wind farm, as towards an engineering constraint. I'm going to focus on these ones mainly on the left-hand side. I'll talk about sediment transport a little bit later, but these are the ones I'm going to focus on with a few examples. So what we've tried to do in our review paper is look at all of these different constraints and hazards, and get a variety of experts in to give their valued input, and reach out to our wide industry and academic community to pull together resources that explain what these features are, and also what they might mean from an engineering perspective, irrespective of what type of engineering you're doing. So that could be carbon capture projects, more oil and gas, or anything, or an offshore wind farm. I think Lena's diagram here is probably going to become the benchmark of geohazard block models going forward. I think it's absolutely fantastic. It just pretty much captures everything in one little model there. Right. So the first one I'm going to go with is the standard shallow gas. So again, shallow gas is a term that's branded around quite loosely. And certainly our experience within my company has been to try and come up with a more firm definition of what we mean by gas and shallow gas. And the reason for that is because a lot of non-geo specialists might get confused about what we're talking about, especially when you're talking about drilling into overpressured units. So we set up I guess a three level characteristic of types of gas. The first is what we call low permeability gas, and a lot of people will call this diffuse biogenic gas or similar terms. But it's basically defined as low porosity permeability sediments that do not have a sufficient concentration of gas to cause an amplitude response in seismic data, but may appear as zones of acoustic blanking or scattering or turbidity, whatever you want to call it. So this is generally associated with I guess gas fronts or low concentration gas within sort of clay material, and it's not under any pressure. There's another type of gas which you can't see on seismic. It's called solution gas, and really this is probably not a massive issue towards engineering projects, but we certainly see manifestations of gas coming out of solution in drilling operations, which can be called fizz gas on occasions. And again, it's not a significant hazard, but it can have some effects on long-term integrity of assets. Whereas actually, what we should be calling shallow gas is truly the overpressured free gas within a trap. So these are the overpressured risks to any type of drilling activity. And although they are generally rare in the shallow foundation zone, they can't be discounted, and certainly are a major concern for at-scale geotechnical borehole campaigns. Just the two images here. The bottom left one is from the central North Sea, from an oil and gas project. Just an absolute classic shallow gas trap there, with pretty much most of the characteristics of gas, high amplitude. It's got a nice trapping mechanism against a fault here. There's some velocity pull down underneath it and a bit of frequency attenuation as well. And it's also associated with a known gas-bearing unit called the Basin Sands, which is quite a prolific gas-bearing unit throughout the central North Sea. So that is a typical what we look for overpressured shallow gas. Whereas on the right, this is sub-bottom profiler examples of this low permeability gas, if you like. And again, it's primarily not under any pressure, but its biggest problem is it actually wipes out all of our high frequency signal, and so we don't get to see any imaging underneath it, which creates a lot of uncertainty in our interpretation. Particularly in where you've got large areas of this type of phenomenon. So the presence of the gas itself, drilling into it, is not necessarily a significant risk to an operation, although it can be if you don't treat it carefully. But what it can do is actually reduce your shear strength quite locally. And so, although the material with the clay, the matrix clay that you're dealing with here may actually be the same, but the gas actually reduces the shear strength in it because of the lack of bonding between the clay grains. If you're going to put a foundation into this type of material, you have to be aware that you may get some long-term strength capacity concerns, particularly if there's a change in the flow dynamics across particular units. And you might get some channeling around the edge of your foundation and some bubbling around your foundations. And some of these may have to be mitigated for. I guess if you've also got larger monopile structures, there is a risk that you could get ingress into the center of the monopile itself. And I know there are systems to bleed off gas from monopile systems for that very reason. One I've just sort of question marked here, that there are some corrosion issues related to certain types of gas. Again, these systems are there in the ground for 40, 50 years. We do a lot of work on corrosion potential, and we do obviously mitigate for potential corrosion in a variety of situations with different coatings of our foundations. But there are occasions in some areas, I mean, where you might not be able to avoid shallow gas, or gas, I should say. And there are a number of areas where, particularly in former estuarine environments or near salt marshes, for example, where you get a lot of peat and a lot of biogenic material, your options to avoid these features become limited. So again, within BP, we have what we call a bubble severity classification, whereby if we're monitoring a borehole or a well, we normally have someone on the rig looking at signs for potential flow and outbreak should we be drilling into something that we don't want to be drilling into. So we've adopted this for oil and gas operations. And again, we have a series of projects where we might want to try to increase our level of certainty that we're not going to have a problem by doing some rigorous monitoring. So we've put cameras down on seabed CPTs, which have then captured low-level bubble flows, just here on the right-hand side. And some of these bubbles have occurred whilst the cone is going in, but most occur coming out. Again, it's low permeability gas associated with peats, and generally we think they've been swabbed in. Certainly in this particular case study here, the pore pressure measurements from the CPT came back as normally pressured. And so we were able to take these observations, classify each of the type of features that we were seeing across our area, and design a geotechnical work program and mitigation plan that would minimize the amount of pilot hole drilling. So we carefully selected a number of locations to do pilot holes, get as much information about that to de-risk the type of anomalies that we were looking at, which gave us the flexibility to then open up our drilling program to a wider distribution. So just because you've got gas doesn't mean it's going to be a problem. I think is maybe not always the case, shall we say. Sort of semi-related to that is the seabed seepage phenomenon. You know, we get manifestations of seepage at the seabed in a whole variety of different styles. I think primarily here in the UK, for example, it's mainly limited to pot marks, but certainly in Norway and in other areas, we get mud volcanoes and significant gas chimneys, etc. So, but I guess, you know, these are again sort of static features. They do have bursts of activity from occasion, and I know many years ago we did some work on trying to predict whether new pot marks could occur and how often they could occur. I wouldn't say we came out with any conclusions on that particular study. So, but you know, I mean, there is something. They are more of a sort of localized constraint, if you like, in terms of cables and placement of turbines exactly where you want them. So, but I think primarily their main constraint is from the environmental side of things. You know, we do not want to be seen to be messing about with these very, very delicate habitats, which is why they're a protected habitat, certainly in the UK. And so they then become a constraint on where you can actually place your equipment and where you can place your infrastructure. You can actually induce some level of seabed seepage as well through our operations as well. So you could get rapid sediment compaction and subsidence related to putting a large foundation in. If the fluid flow is particularly vigorous in the subsurface, you could get subsurface cavity formation, and then liquefaction. So I've included gas hydrates here. So in my experience in deep water oil and gas projects, we encounter gas hydrates all the time. And they do have an element of threat to certain parts, certain operations. They're a deep water phenomenon if you're not familiar with them, and it's basically just gas and water in a solid state that is very susceptible to subtle changes in pressure and thermal gradient. And certainly changes in the localized thermal gradient can cause melting or dissociation of these hydrates. And at scale, that can be a very significant threat for potential landslide activity. But because these are basically sort of like almost impermeable solid blocks of ice in the subsurface, they often actually create a trap for shallow gas below the stable hydrate. And the images on the right give you a few examples of what we call a bottom simulating reflector. That's a really good indicator that you've got free gas below stable hydrate. Normally, you know, this is normally below, relatively, depending on thermal gradient in the area, it's going to be below your foundation zone, but not always. And although it's not a phenomenon for shallow water, in deeper water, as we start to move into more floating wind options, this could become a lot more important, not only in terms of foundation capacity and long-term integrity, but also as again it becomes a bit of a risk in terms of localized landslide activity. But if I'm honest, it's still unclear to me what impact it might have on foundation design and installation. And the reason I say that is because, as I said, as an oil and gas developer, we've encountered gas hydrates in a number of engineering projects. Yes, we've had some longer term bubbling issues related to destabilizing of hydrates related to produced fluids. But in terms of putting foundations in the ground, we've managed to install suction caissons and piles, and generally without any issue whatsoever. So I think this is a watch and see what happens when we do start to encounter them. I think one that is very, very, I guess, important, not only for foundation design, but also more importantly, from my perspective anyway, is on the installation side of things. And that is the variability in soil strength. As I said, these sedimentary environments that we're dealing with in glacial margins are extremely dynamic and change rapidly from a clay deposition to a sand deposition, with different levels of compaction and you know and property change, and the threat of what we call a strength inversion in these environments is very high. So in the top left-hand image, we have a CPT profile through a series of channels. The upper part is very dense sand. Then the shear strength drops off for about 4 to 5 meters to very low strength clay, and then back into very dense sand. If you have 5 meters of very dense sand and then 4 to 5 meters of clay, that is not a good place to be if you want to put a jack-up rig on the seafloor, because you could quite easily get an immediate 4-meter punch through that material. So this has to be carefully monitored and measured, and ensure that we understand the soils to avoid instances like this that happened in China in 21, where although the information about the exact cause, I think it's pretty obvious that it's had a leg foundation issue. Sadly, 4 people were lost at sea from this particular incident. And I think we in the oil and gas industry, we take this very, very seriously, but generally we're only looking to bring one rig in to one location to drill one well. Here we're bringing jackups into locations multiple times at multiple locations. So it really is, you know, should be given a lot more focus, and certainly taken seriously as a potential threat in this type of scenario. That's just from the rig foundation perspective. Obviously, if you've got then, you know, if you've got incorrect assessment of your required foundation weights and lengths, etc., where you get soils with lower strength and characterized and designed for, during installation, you may suddenly get an overly heavy pile that suddenly meets a weak material. And I don't know if you've ever seen a video of pile run. It's quite impressive, and you'll just suddenly lose your entire pile in one instant. On the flip side, obviously, where you've got soils that are significantly stronger than anticipated, or you might encounter some obstructions, pile refusal is relatively common and an issue. You may have to rerun piles, or you may even have to drill them out, which is extremely costly. Then on the cable side of things, the geospatial variability of soils again sort of controls where you plan your cables, because suddenly going from a relatively strong sand or a strong clay into a very weak soil, weak clay, you can easily damage your equipment. You've got variable depth of burial, and in some cases you can actually damage or lose your equipment completely. Just as a sort of theoretical, I guess, other avenue to look at in terms of soft sediments, most projects have up to now anyway have used either monopiles or a series of jackets with piled structures, but a lot of also starting to look at or have used gravity-based structures. So I just grabbed some images from a really nice video by Van Ord here down the bottom, which goes to show the preparation of ground in preparation for putting a gravity-based structure in. I was hoping to put the link in here, but I forgot to do it, so I apologize for that. Maybe if I find it in the chat, I'll post it in there. But essentially what you have to do for a gravity-based structure is prepare the ground so that it is completely and utterly flat, and that you have a predictable, I guess, soil profile across the footprint of the gravity-based structure. So these gravity-based concrete cones, if you like, several thousand tons in weight, variable diameters, some up to 35, 45 meters in diameter. So essentially you have to dredge out the material to get a flat base. You then have to put a rock pad or a gravel pad on top of that with sufficient, I guess, room for maneuver, shall we say. So you have to spread your gravel out to about 3 or 4 meters beyond the footprint of the gravity-based structure, and then put scour protection around it, and then you can put your structure on top. So ideally what you want, say in a scenario where you've got a 35-meter wide gravity-based structure, is you want to dredge down to about 1.5 meters and go out to around about, let's say, 45 meters. But if you encounter sufficiently soft clay, so this scientific example shows that we've got some soft clay material over sand, your preparation area increases exponentially in order to be able to cope with both the horizontal sliding capacity and the bearing capacity of that particular structure. So you may even end up going like 20% further out and deeper, and certainly that increases your cost, and also and it very quickly becomes uneconomic, and therefore becomes a very, very significant hindrance to your development. But yeah, just again, a lot of people don't realize exactly how much preparation the ground has to have for these types of engineering projects. So it's important to bear in mind. Another quick case study here from the Danish sector, very kindly provided by Vattenfall. So this is the Horns Rev 3 development in the Danish sector, inaugurated in 2019. It's a 49 8.3 megawatt turbines, situated on a post-glacial silt unit of low strength and a high liquefaction potential. Under stress and strain, the soils will liquefy, just as you happens to your sand under your feet at a beach when you're standing there for a long time. So just a series of time-lapse images here on the left-hand side, in the middle here, sorry. Pre-installation bathymetry from 2025, no issues, nice flat seabed. And it also sort of shows you again here on the profile. You can sort of see there is some, I guess, low concentrate, low permeability gas, or certainly blanking within the area. But generally the geology is fairly straightforward. In March 2018, post-installation of the turbine, a repeat survey showed that there were some significant depressions caused by the jack-up rig, or certainly where the jack-up rig was, and also that the scour protection of the turbine itself has been cut into and compromised. So repeat surveys were done over the next over that year to sort of monitor what was going on, and the situation was gradually getting more significant. More and more material was getting moved away or being redistributed. So eventually, obviously, at this point, they realised they had to do something. They had to remediate the risk of this turbine destabilising. So, not exactly sure what the engineering solution was, but it would have almost certainly been some level of rock dumping and gravel padding, rebuilding the scour protection. And again, the cause is unknown, but it's likely to be related to multiple jack-up operations going into the location, usually involving some sort of jetting around the legs to make sure that it's clear, nice flat surface. But it could have also been generated through repeated storm events through the year 2019. But I think it just goes to show that, just by the dynamic, I guess, processes that are ongoing, not only by what we're doing to the seabed, but also from nature in terms of currents and storms, it can quickly go south on you if you're not monitoring it. Boulders. Just check the time. Need to rattle on. Sorry. So a pet subject of mine is boulders. I have mixed feelings about whether boulders are significant or not, but and I think that probably comes down to the experience of projects that I've been involved in. But boulders are very common, or can be very common, in glacial environments, associated with particular depositional systems, and also their proximity to the ice in order to be able to actually move a boulder. They can cause early refusal in site investigation programs. If anybody's tried to do a CPT in some of these areas and you come up with a 2 centimeter bent cone, you know that you've hit a boulder. It can hinder pile installation, get refusal, damage, deflection of the pile. Seabed boulders can damage the spud can, jack-up spud cans, cable routing constraints, etc. And certainly the cost of having to remove boulders of significance can be significant. Can be very costly indeed. Boulder detection is inherently perilous. It relies on being able to visualize them and identify them using remote systems. And our common system of choice is 3D seismic, or certainly seismic data and sub-bottom profiler data. And we are looking for things like what we call seismic diffractions. So these little spots in the data, and these little diffractions here, which when you see them, it's pretty obvious. The problem is that there are multiple sources in the subsurface geology that can cause diffractions. And so you get an awful lot of false positives if you're interpreting this. And as I said, not necessarily will a diffraction be a boulder. And on the flip side, you've got a geotechnical borehole here, which has actually sampled over 60 centimeters of metamorphic schist, with absolutely no indication of a boulder being present at all in the seismic data. So it's this sort of chicken and egg scenario where you're acquiring data where I hope you're going to see a boulders, and you don't, and yet you've also got the chance of hitting a boulder in seismic data where you don't see it, which is again why I find it problematic when it comes to identifying boulders. On this particular example, sorry, just as an aside, we're going to come on to landforms in a minute, but there are 2 other hazards or features, constraints, shall we call them. The first one down here, this is an ESCA. We'll talk about those in a minute. But this is an interesting little localized phenomenon in the west of Shetland. Most people say, oh, that's a channel. When you actually look at it in profile view, it's basically just a hole created in the paleo seabed, and it's where ice has actually carved off the front of the ice shelf, scoured into the ground, and which is then quickly filled in with, I guess, outwash material. And certainly what we found is these can be very, very localized, loose, unconsolidated sands within an over-consolidated clay matrix, which has a significant impact on pile design. Just a little bit more on boulders. again, I find them quite challenging in terms of how we go about identifying them, how we go about predicting them, and how we communicate our level of threat to engineering. Ultimately, I'd love to have a picture like this on the right-hand side where you actually get a nice photograph of the boulders. That's easy. You can tell that those are boulders 30 to 40 centimeters wide. The same area on the multi-beam sonar, it's a bit trickier to tell. But certainly an approach that we've taken in the past is to do a more qualitative probabilistic assessment based on the type of depositional environment, but also sense checking that against some automated and manual boulder picking. And then just coming up with some probabilistic hit maps of where boulders are likely to be, and therefore, focusing in on moving away from the highest concentration to where you might have a greater success in avoiding them. Okay, depending on where you are, you might eventually have bedrock within your area of interest or depth of interest. Bedrock is generally the enemy. We generally don't like bedrock in terms of foundation design. It's not always your enemy, but it generally is. Strong rock head will cause pile refusal, damage to the piles, inclination issues, and cable burial refusal. But in situations where that rock has been exposed to other processes, i.e. periglacial environments or subglacial weathering processes, it can physically change the property of the rock to become your friend. And certainly, particularly where you've got soils such as the Mercia mudstone, for example, or similar material, the weathering process can actually change those geomechanical properties to allow those to be driven into just as equally as easily as any other sort of clay-like material. I think one of the problems that we do have from a seismic geophysical perspective is it's not always straightforward to predict the boundary between what is clay, what is weathered bedrock, and what is actual bedrock. On the bottom here, we've got an example of evaporitic mudstone. Up here, the top image is completely and utterly weathered. It's basically just residual soil now. But at depth, you're still sort of seeing alteration in changes in the properties until you go right down to the base here. But actually, there isn't much indication. You could sort of say, well, okay, there's a fuzzy zone at the top, which may indicate that's the higher level of weathering, but there are multiple reasons why you've got reduced imaging there as well. And then occasionally we have to play the game spot the bedrock. So depending on the material, the bedrock material, and the then I guess subglacial deposits derived from that that bedrock material, the differentiation between the two can be quite challenging. So again, this is what's called the Irish Sea Till. It's primarily a glaciotectonite derived directly from Mercia mudstone, which is why they look almost identical. This is the till on the top. This is the weathered mudstone at the bottom. So we got a nice CPT through this, and the till itself is pretty boring in terms of physical properties. It's predictable. It's got a very predictable profile, and then it goes into the mudstone, and we get a bit more variability. We then go and look at the seismic data, and this is pretty good quality seismic data. This is 3D. And I think most people even would sort of say, well, okay, there's the top of the bedrock down there, that big strong reflector. Yeah, probably. When you superimpose the CPT on top of it, you can sort of see that the change of the CPT response is midway through this completely structureless unit. Again, you have to remember the difference between geophysics and geotechnical data. The geotechnical data is actually physically sampling, whereas the geophysics is I guess a physical representation of a change in velocity and property. So, as I said, the two materials are actually quite similar in terms of both appearance and also what they are on the geotechnical, what they are on the seismic data. But geotechnically, they are quite different. and that is very challenging to map out from a ground model perspective. Peat. I'll try and rattle through this one because I think we're running a bit late on time. So peats, again, can become a significant constraint, tend to be sort of in areas where I guess we're formerly estuarine in nature or pretty close to paleo shorelines and salt marshes. They can be extremely widespread. And basically, if you've sort of seen peats on the shorelines around our coastlines, you can tell that they can be quite variable in their structure and their nature. They can be quite fibrous. They can be quite loose. They're highly compressible. But their biggest constraint is they are a thermal insulator. And so what that means is that if you encounter them, if you bury your export cables or your inner array cables through peat, because those cables generate a huge amount of heat during their transmission, any subtle changes in the material around the cables can cause those cables to burn out or to suffer from poor performance. And so our ability to identify peat is critical mainly for cables, but it does have aspects of hindrance to other operations as well. And certainly one thing that doing some research on the Paleo Elbe Valley, H2S production from degradation of peat and organic material, you can actually get quite high levels of H2S being produced, which is not great if you're on a rig and you drill through it and you suddenly start smelling bad eggs. It can be, well, it is extremely poisonous, so we don't want that happening at all. But also it has a strong corrosive effect on both cables and any other steel structures. Glaciotectonism, as I said, it's not just about deposition, but it's also, this is a very dynamic environment. We're dealing with ice sheets coming backwards and forwards, loading and unloading, altering the fabric, changing the structure. Again, it's all around local variability in predicting soil conditions. Even with high quality geotechnical data, you're not going to be able to capture every single possible scenario in terms of strength profile in an environment that has been suffered, I guess, or tortured so much as a subglacial deposit. You can also get quite large rafts of I guess, exotic material, if you want. So very large blocks of material that have been brought, either soil or even blocks and rafts of bedrock have been moved kilometers away from their original position. You know, and so again, it's just another demonstration of how unpredictable a glacial environment can be. And associated with that, again, we've got some very localized features, landforms, different types of landforms. Here we've just shown an example of an esker. An esker is basically a subglacial, I guess, water channel in the bottom of the ice, which is then later shut off for some reason. The water flow is shut off, and then it becomes infilled with sediment. Again, you get very, very localized and different, very different properties and soil types within these features, and they're a lot more common than we first anticipated. I think, unfortunately, you probably do need 3D seismic data to identify them confidently, but you know, that's the benefits of going 3D. Just some more examples of the variety of landforms that we have. Just an example here in the top left-hand corner, two seismic images. I'm looking at the surface unit, and the base of the unit is characterized by this sort of lumpy, ridgy-like or hummocky-looking pattern. On face value, you'd sort of say, well, those are the same deposits. They look the same acoustically. They've got the same basal feature. But again, when you map them in 3D, the one on the left-hand panel B here it forms three-dimensional geometric ridges, whereas this one on the right-hand side forms subsurface iceberg plough marks. Why is that important? Well, on the left-hand side, this one is what we call crevasse squeeze ridges. So we know that these were created by an advancing or a surging ice front that's come into a lake system, latched onto the base of this previous deposit of clay material and squeezed that material into the bottom of the glacier and the ice sheet, and therefore physically changed the properties of the underlying clay. So it's gone from being a relatively soft clay to an over-consolidated, fractured, folded, and foliated clay. Again, important to understand from a geotechnical perspective. On the other hand, with the iceberg plough marks, they're just grooves. And so geotechnically, there's no difference between that really. It's just a moment in time that has caused these things to occur. And then seabed mobility, very, very important. Our seabed is highly mobile. It's a lot of features there that can cause phenomenon around both our foundations and anchors. Scour protection is critical to protecting our assets. But likewise, material moving around the seabed is either going to bury our assets or expose it. And again, that has repercussions for long-term engineering and integrity and occasionally remediation as well. I'm going to skip that one. Let's quickly talk about this one because I like this slide. To 3D or not to 3D is a good question. So I think historically everybody's gone into these projects by thinking, okay, you know, we don't even know if we've got a project yet. Management are pretty keen for us not to spend too much money. So, but we need something. We need to understand the site. So our general first port of call is to go out and do a regional 2D survey. So this image on the left-hand side pretty much shows you what you would see if you went ahead and did a box of 500 meter by 500 meter 2D data. Great. I can see things. I just don't know what they are. What you could do then is either do some infill or do some interpolation to try to create a three-dimensional surface out of that. And by doing so, you can start to see some variability in the properties or in the features that you're seeing. But again, you'd have to be pretty confident that in your ability to then say, okay, well, these features are important or not. But if you were lucky enough to persuade your management to then give you the money to go and get your 3D, that is when you can actually start to pull out the true detail of the area. You then understand, you know, all of the dynamics behind what's going on behind the deposition and subsequent erosion and alteration, and you're much more, higher degree of confidence that you understand what you're engineering into, and it also then gives you a greater flexibility to microsite and move away from these things. So business justification for that, well, we all want thoroughbred data, you know, we all want 3D, but it's not necessarily the answer, and it does come as a cost. But, you know, people ask me, how did I get 3D for a certain project? Well, it was a simple equation. Is it better to spend million now or millions down the line through either litigation or contract variation and reducing your uncertainty? And certainly when you're dealing with very, very difficult ground, that conversation can actually be quite easy. But generally, you just really have to go for what fits your purpose, and sometimes that could be the beach donkey, which is perfectly okay for that type of environment. So that's pretty much it. That's me. I've run out of time. I'm sorry, I didn't practice well enough. But so essentially, our role as a geoscientist, as it says here, is to understand the ground, and you know, we try to communicate potential levels of threat to both design, installation, but also to the long-term integrity of our assets by generating ground models. But in my view, a ground model should be much more than just a series of units and physical properties. It should also talk about the geological history. It should talk about the processes and, more importantly, capture the uncertainties in that interpretation of ground model, which is perhaps something as a community we're not very good at. And I think one of the differences between an oil and gas project and an offshore wind project too is that generally you can move your infrastructure in an oil and gas project to avoid certain features, but that is not always the case in offshore wind, and sometimes you just have to work with the ground you're given, and sometimes that's a challenge. So with that, just want to say thank you very much, and it's been a pleasure talking to you all.
Thanks a lot, Gareth, for a very interesting and detailed presentation. Isabella, right? Do we have still some time for some few questions? Is that okay?
Yes, for sure. We can take 10 minutes for questions.
Okay, let's take some minutes, 10 minutes you suggest. You got quite a lot of questions, Gareth, especially related to gas. But let's start. We cannot address all of the questions in this 10 minutes most likely. However, we will forward the questions to Gareth Wood, and he may most likely respond to them, and we can forward you the responses after the Gareth has been able to answer them. But let's start with those who got most of the likes. So there's a question from Susan Rice. Speaking from the site survey industry, how can we best communicate the heterogeneity of soils when we're typically required to just pick base of formation units? Or is it just about best left to the integrated ground model? Even then, soil provinces don't always do justice to what we see on the seismic data.
Yeah, Susan, great question, and you hit the nail on the head, really. It all comes down to your flexibility in producing your scope of work in the first place. So if the developer writes a scope of work to sort of say just pick this, that sort of restricts you straight away, and so you just do what you're asked to do. The way I work is to throw all of that information out and look at what I've actually got, and try to think rationally about what is important for the project in terms of what are the features that are needed. And if that means I have to produce 3 or 4 different ISOPAC maps, or have to map out things a little differently, then that has to be done. But I think what you then have to do as a survey contractor is go to your client and demonstrate why it's important, why you think it's important, to deviate from the scope, and hopefully that communication line will open their eyes, and you would eventually deliver a much better fit for purpose product because of that.
Thanks, Gareth.
Good. Another question goes more into the seismic blanking. You showed several examples where we lose signal due to the gas. So there's a question from Vicky Freeman. Have you found any geophysical methods to see through past low permeability gas? And there was already an answer, like an indication that potentially EM methods could work to fill gaps. What is your opinion on that?
Yeah, it's extremely challenging, that is for sure. Ultimately, the only way to get through, I guess, diffuse gas like that is to use a different type of source, maybe one with a wide range of frequencies rather than a standard sort of set frequency range. It is because the high frequencies are getting scattered by the bubbles of gas, and it's very difficult then to design a system that can deal with different sizes of those bubbles, if you know what I mean. So usually the case is just to go for a bigger source and hope you get through it, but then you lose your resolution. There are occasions, certainly in again in the oil and gas industry, where we've tried to image underneath other obstacles by using I say undershooting techniques, where you can have your sources on one side of the feature and your receivers on the other side, and then try to shoot in a pattern to image underneath. But that's extremely time-consuming, costly, and not really beneficial for this type of activity. It's a challenge, I'm afraid.
Good. Still some challenges to look at, for sure. Let's go into a question from Nayan Hubai. It's a question on cables and pipelines. So based on your experience, what are the most common or the most problem-causing geohazards for seabed cables and or pipelines? Thanks a lot for the seminar.
I think the biggest, certainly on the continental shelf and shallower water, is our mobile sediment. You know, in our currents. There's not much we can do about stopping the sea from seabed currents moving around. They, you know, and particularly with cables, electrical cables, for especially where burying them or exposing them, even by a very small amount in terms of burial depth, can affect their performance and their long-term integrity. Yeah, for me, it's probably seabed mobility. But that's not always the case everywhere, of course. And so, I mean, likewise up in west of Shetland, where we've got a boulder every 30 centimetres, that's a big issue, because then you've got to remove all those boulders to then lay a cable or a pipeline. So it does very much depend on where you are, but yeah, that's, I would say, seabed mobility.
Thank you. Then we do two more questions. One from Seal Mossel. So it's written that understandable that this is applicable for large gas pockets in deep oil wells, but how much pressure can you realistically get in seabed CPTs or down the hole CPTs for offshore wind installations, maximum 100 meters into the subsurface, for it to cause a hazard?
I missed the last bit.
Yes, so it's I can repeat it.
No, I heard a bit about CPTs, pore pressure. It was just the last sentence I missed.
Okay. Yeah, maybe I can just repeat it. Understandable that this is applicable for large gas pockets in deep oil wells, but how much pressure can you realistically get in seabed CPTs or even down the hole CPTs for offshore wind installations for it to cause a hazard with respect to the uppermost 100 meters?
So that's a good question. I mean, a pore pressure isn't necessarily. I don't think we could say that pore pressure is considered a hazard in its own right. I mean, it's really important to understand the variability of pore pressure for you know, for understanding soil properties and for design. There are occasions where we could get some level of overpressure in the shallow section, but generally it's we're not talking about the same types of overpressures that we are for deeper sections. It's more around changing the localized physical characteristics of the soil, where you might get a localized spike in pore pressure that has to be taken into consideration. So with those downhole CPTs, they are measuring pore pressure quite accurately. So even a slight rise or decrease can look quite dramatic on it. It just doesn't necessarily mean it's an engineering constraint in its own right. It's just what it actually means for the soil. But if there is any sort of buoyancy effects of having gas within a shallow reservoir, you will see that in the CPT as well. But it's not the same as a significantly overpressured gas anomaly at depth.
Excellent. And then the last question. Again, we will share this the webinar on the YouTube channel later on. But the last question comes from Niklas Olerichs, and he's asking, following the definition on the low permeability gas as anomaly of acoustically anomaly visible on sub-bottom profiler data, would you refer to amplitude anomalies with acoustic blanking below, as often seen in ultra-high res seismic data, as low permeability gas as well?
If that particular concentration of gas is sufficient to cause an amplitude anomaly, then yes, you would call it. Yeah, you could call it you know, an amplitude anomaly or a high amplitude anomaly. But then you then need to evaluate whether it's overpressured or not. And I think the key thing, what we try to do, certainly in my part of the business in BP is trying to communicate the difference between what is the risks posed or the threats posed by an overpressured shallow gas pocket that's at depth or has sufficient buoyancy to then be unable to control that as you drill through it. So you may have a very strong amplitude response from a low permeability unit that's got quite a high concentration of gas, because it's basically still just the physical acoustic impedance contrast between the two interfaces, but it's not under any pressure, and it shouldn't cause, well, in most cases it shouldn't cause you any problems. But that's not to say that you don't look at it carefully, you don't evaluate carefully. If you've got the ability to measure pore pressure through it to de-risk it, then that's a good way forward.
Excellent. Yeah. Thanks a lot, Gareth, for all of this these insights. And again, we will share this webinar. Isabella will do that, and via the EAGE YouTube channel. And also, we will forward the questions that we did not address now to Gareth, and we'll provide you with the answers. Yep. And otherwise, yeah, don't forget about there will be a dedicated session on this topic at the annual EAGE, and most likely a full-day workshop during the GET in Hanover. We have not gotten a response yet, but in case you're interested, these are definitely places to meet and discuss. And yeah,